12-inch wire will be cut into two parts such that one part is bent into a square and the other into a circle. If the wire used for the square is x inches long, express the sum of the areas of the two figures in terms of x. So let us first illustrate the problem. So we have a wire which is 12 inches long. Now, it will be cut into two parts. So let's put a mark where the wire will be cut. So suppose this is the portion where it will be cut. One part will be x units long. So to get the length of the remaining part, we will subtract x from the original length of the wire. So we get 12 minus x. Now, according to the problem, the wire having a length of x units will be bent into a square. So since a square has four sides, we will be dividing x into 4. So each side will have a length of x over 4. So let's illustrate the square. And the side of the square, suppose we use s to represent the side, it will be x over 4 units long. So S is the side of the square, or the length of the side of the square. Now the other part, or the other wire, will be bent into a circle. Suppose this is the circle. So 12 minus x will become the circumference of the circle. And let's use C to represent the circumference. It will be 12 minus x. So C is the circumference of the circle. Okay, now we are required to get the expression for the sum of the areas of the two figures. Let us use A to represent the sum of the area, or the areas of the two figures. Okay, so let us solve the problem. A now will be equal to the area of the square plus the area of the circle. So let's use A1 for the area of the square. And A2 for the area of the circle. And we want the area to be in terms, the area of the square plus area of the circle to be in terms of x. So we have A will be equal to A1 plus A2. Now for the square, we know that the area of a square is equal to the square of its side, or the length of its side. So since the length of the side is x over 4, A1 will be x over 4 quantity squared, or x squared over 16. Now for the circle, A2, we know that the formula for the area of the circle is pi r squared. However, we need an expression that is in terms of x. So we need to replace the radius with an expression in terms of x. So we will be using the circumference. We know that the circumference of the circle is 2 pi r, and it is equal to 12 minus x based on the given. So here r is 12 minus x all over 2 pi. Therefore, A2 is pi times the square of the radius, which is now 12 minus x all over 2 pi. If we square this, we have pi 12 minus x squared all over 4 pi squared, and we can cancel pi, giving us 12 minus x quantity squared all over 4 pi. So we now have an expression for A1, And for A2, we will be substituting this to A1 plus A2 and get the sum of the areas of the two figures. So A will be A1, which is x squared over 16, plus A2, which is 12 minus x quantity squared all over 4 pi. So this is now the area in terms of x, the sum of the areas of the two figures in terms of x. A box with an open top is to be constructed from a rectangular piece of cardboard with dimensions 12 inches by 20 inches by cutting out equal squares of side x at each corner and then folding up the sides as in the figure. Express the volume V of the box as a function of x. So to illustrate the problem, we have here a cardboard having dimensions of 20 inches and 12 inches. Now, we will be cutting out squares from each corners having a side of x. So these squares will be cut out and the remaining figure will be, we will be folding the remaining figure and seal the edges to form this box. And we want to get the volume of this box in terms of x. So let us write our required in the problem. So volume of the box in terms of x. Let us represent that as v of x. So let us solve. We know that the volume of a box will be the product of its length, width, and height. However, since the problem requires us to write it in terms of x, we need to find expressions for the length, width, and height in terms of x. So we refer to the cardboard in the illustration. Suppose we are going to associate the length of the resulting box from the 20 inches side, and then the width will be associated with the 12 inches side, and we know that the side of the square will now become the height of our box. So this portion here will be the height of the box, and this one will associate this with the length, and this one we will be associating with the width. So this will be the width of the box, this would be the length, and this one would be the height. Alright, now since the height of the box will be associated with the square taken out from the cardboard, we know that this will be x units long. On the other hand, the length will be associated with the 20 inches side of the cardboard. Since we will be taking out two squares from this side, the resulting length will be 20 minus x, or 20 minus 2x. Now, the width will be associated with the 12 inches side of the cardboard. And since we will be taking again two squares from the corners, the resulting width will be 12 minus x, or 12 minus 2x. We will now use this to and substitute to the volume of the box. So we have V is equal to 20 minus 2x. The width will be 12 minus 2x. And the height will be x units long, or x inches long. We can now write this as v of x since we now form an expression that is purely in terms of x. So we have v of x is equal to 20 minus 2x times 12 minus 2x times x. So let's say we want to um, multiply each of these expressions. So we will have 20 minus 2x times 12 minus 2x. So let's distribute. So 20 times 12 gives us 20 times 12 gives us 240 minus 40x minus 24x plus 4x squared. And then we still have an x outside. Let's distribute that as well. So we get 240x minus 40x squared minus 24x squared plus 4x cubed. Let's just rearrange. So we have 4x cubed, and then combine similar terms. We have minus 64x squared plus 240x. So this is now the volume of the box in terms of x. A farmer has 400 meters of fencing material to enclose a pen shown in the figure. Express the total area of the pen in terms of x. So in this problem, we are required to express the area of the pen in terms of x. Now, to solve this, we have, by the way, we could represent the area of the pen in terms of x as a of x. So first, we write it as area, or a, and we know that for a rectangular pen, as shown in the figure, the area will be equal to the product of its length and its width. So if we refer to the given figure, the length will correspond to this side, and it is 2x units long because you have x plus x. And then the width will correspond to this side, which is y units long. So we have the area is equal to 2x times y. Now, since we want our expression to be purely in terms of x, we need to find an expression uh, for x, for y in terms of x. So we will be using the given um, length of the fencing material, which is 400 meters. So 400 meters will be utilized to construct all the portions, all these portions for the rectangular pen. So this will be equal to, so 400 will be equal to this x here plus this x, including the ones at the back. So you have a total of 4x plus these three sides here, each having a length of y. So that's a total of 3y. So y plus y plus y, or 3y. So given this one, we can find that y is equal to, so first we transpose 4x. So we have 400 minus 4x will be 3y, which means y is equal to 400 minus 4x all over 3. We use this and replace y in the formula for area. So we have 2x times y, which is now 400 minus 4x all over 3. So giving us, we distribute 2x, so we get 800x minus 8x squared all over 3. So now we were able to come up with an expression for the area of the pen in terms of x. So we can now write it as a of x. It is equal to 800 minus x minus 8x squared all over 3. A cone-shaped drinking cup will be made from a circular piece of paper with center C and of radius 10 centimeters. This will be done by cutting out a sector, then joining the edges CA and CB, as shown in the figure. Express the volume of the cone in terms of its height, h. So, to solve this problem, we are required to write the volume of the cone or the conical cup in terms of its height, h. So, let us denote this by V of h. Okay, so we know that the volume of a cone is equal to 1/3 pi r squared times the height. Since we want this to be in terms of h, we need to find an expression for the radius in terms of h. So h here is the height and r is the radius of the cone. And if we illustrate that, so this will be the radius of the cone and this will be the height of the cone. Okay, now we refer to the given figure as mentioned in the problem, a sector. So this is the sector that will be cut out. After that is cut out, the edges CA and CB will be sealed or joined together. So that portion will be, if you use this cone here, this will correspond to the edges of CA and CB joined together. And this will be equal to 10 centimeters because that would be the radius of our circular piece of paper. Now, going back to the formula of the cone, we need to find an expression for the radius, and then referring to the figure of the cone, we know that we can use the Pythagorean theorem to relate the radius, the height, and the slanted height of the cone, which is 10 centimeters. So we have 10 squared is equal to r squared plus h squared. So this one is also 10 centimeters long, which is the slanted height of the cone, and it corresponds to the hypotenuse of a right triangle having bases r and h. So in this case, we find that r squared is equal to 100 minus h squared. We will use this to replace r squared in the formula for the volume of the cone. So we write 1/3 pi, instead of r squared, we write 100 minus h squared times h. So we are now able to form an expression for the volume of the cone in terms of height only. So we can now write this as v of h, and we have 1/3 pi. Suppose we distribute h, we have 100h minus h cubed. So this is now our expression for the volume of the cone. A Norman window is shown in the figure where a semicircle is mounted on top of a rectangle. If the total perimeter of the window is 16 feet, express the area of the window in terms of x. So in this problem, we are required to express the area of the window, let's say A, in terms of x. So we can denote this now by A of x. So we solve. So we can write A as the sum of the area of the components of the window, which is a rectangle and a semicircle. So let's use AR for the rectangle or the area of the rectangle, and then AS for the area of the semicircle. So AR, so this is area of the rectangular component of the window, and AS for the semicircle component. So we write AR, we know that the area of a rectangle is length times width. So based from the figure, let's use x for the length of the rectangle and then y for its width. Therefore, AR is x times y. AS, on the other hand, we know that the area of a circle is pi r squared. Since this is just a semicircle, we divide that in by 2, so we have pi r squared over 2. Now, we want the formula for area to be in terms of x only. So we must find an expression to replace y and r both in terms of x. For the radius, it's easy to see that the radius of the semicircle is x over 2. Now, for y, we are going to use the perimeter given for the window, and that would be 16 feet. So the perimeter of the window is 16 feet. And this accounts for the outline of the window. The outline of the window is composed of the three external sides of the rectangle. So this side here will not be used because it's inside the window. And we will also include the semicircle component of the window. So the perimeter will then be equal to x for the base of the rectangle, and then the two sides of the rectangle would be y plus y, or simply 2y, and then the perimeter of the semicircle is 2 pi r over 2. So 2 pi r is the perimeter or the circumference of a circle. Since this is a semicircle, we divide that by 2, so we get pi r. Again, we note that the radius is equal to x over 2. So we have pi times x over 2. So we transpose all terms except 2y on the left side of the equation. So we have 16 minus x minus pi x over 2 is equal to 2y. And then divide both sides of the equation by 2. So we get y on the right side and on the left side. So we divide everything by 2. So we have 1/2 of 16 minus x minus pi x over 2. So let's continue. We now get the area of the window as AR. So AR is x times y, but instead of writing y, we have times 1/2 times 16 minus x minus pi x over 2 plus pi r squared over 2. However, the radius is x over 2, so we have pi x over 2 quantity squared all over 2. So let us simplify this. We have x times 1/2 is 1/2 x, and so we have 1/2 x times 16 minus x minus pi x over 2, plus we have pi over 2, and then x over 2 quantity squared is x squared over 4. So we distribute 1/2 x to every term in this expression. So we have 1/2 x times 16 gives us 8x, minus 1/2 x times negative x is negative x squared over 2. Negative 1/2 x times negative pi x over 2 is negative pi x squared over 4, plus pi over 8x squared. So notice that the last three terms are all in terms of x squared. So we can factor out x squared and we get 8x, or we can actually factor out negative x squared. So we have 1/2 plus pi over 4 minus pi over 8. So simplifying, we have 8x minus x squared. So 1/2 plus pi over 4 minus pi over 8, we can combine that. The LCD will be 8. So we get 4 plus pi, or plus 2 pi, minus pi. So finally, we can write our expression in terms of x. The area of the window, A of x, is equal to 8x minus, so 4 plus 2 pi minus pi is 4 plus pi all over 8, and then you have x squared. So this is now the area of the window in terms of x.
Experimentation to come up with an empirical formula. The Mauna Loa Laboratory in Hawaii records the carbon dioxide concentration Y in parts per million in Earth's atmosphere. The January readings from various years are given in the succeeding table. So to create an empirical model for the amount of carbon dioxide in the atmosphere from 1960 to 2020, we are going to use the graphing software Graphmatica, which you can now see on your screen. So once you've opened Graphmatica, you go to the View tab and click that and look for Data Plot Editor. So you click that and you will be able to plot the points that you need for this model. So for the x-coordinates, we are going to use the number of years from the starting year, which is 1960. And then for the y-coordinates, we are going to use the amount of carbon dioxide in the atmosphere. So since we started at 1960, so we are going to assign 0 to that. And then the amount of carbon dioxide was recorded to be 316.43 parts per million. And then 1970, so that's 10 years from 1960, so we put in 10. And then the amount of CO2 is 325.03. 1980 would be 20 years from 1960, so we put in 337.9. And then 30 years from 1960, we have 353.8. So year 2000, so that is 40 years from 1960. So that is 369.29 parts per million. 2010, so that would be 50 years from 1960, so 388.71 parts per million. And finally, year 2020, so that is 60 years from 1960. So the recorded carbon dioxide in the atmosphere is 413.39 parts per million. Okay? Now, notice you do not see the points on our plane because the values are quite large. So we are going to adjust that by going to the View tab and then click Grid Range. So we are going to adjust the values. So for the left and right, this is for the for the x-axis. So that's okay. -8 for the left side is okay. But for the right side, since the maximum value is 60, so we could use 60 or give an allowance. So let's put in 70. For the bottom part, that's all right, -4.31. Now, for the top, meaning above the x-axis, since the largest value that you see is 413, so let's just put in 450 here.
and then click OK. So now you see the points that you have entered in the data plot editor. So now we want to find a curve that closely fits this data set. Okay, so you're going to use curve fit, but first you have to click options so that you can set what kind of graph you would like to use. So for this discussion, we are going to use a polynomial. So let's try first if we make it a linear function. So the maximum order of a polynomial which is linear is 1. So we click OK. And then you click curve fit. So now you have created a line. So if you click the line, you would see at the top portion the function that would represent this line. It is equal to y equals 1.6058x plus 309.6182. So notice that there is a value of r which is equal to 0.9894. So that gives you an idea whether the model that you have created gives a good relationship among the data set. So if it's very close or if it's close to 1, then the model is shows a good relationship between the data. So this is for the linear function. Now, suppose you want to try a different function. So you go back to options. This time, I want to try a quadratic function. So I will be changing the maximum order of the polynomial to 2 because that's a quadratic function. So I'll click OK and then press curve fit. So I will just remove the line so that you can see the parabola. So this is now the graph of the parabola, and to see the equation for this parabola, you have y is equal to 0.0134x squared plus 0.8035x plus 316.3043. And the value of r squared is 0.9994. If you get the value of r, if you take the square root of that, it's also around 0.99, which is closer to 1 as compared to the model, the linear model that we created earlier. So that means the quadratic function is a better model in terms of showing the relationship between our variables. So the resulting equation now is the mathematical model is an empirical model that describes the relationship between the number of years from 1960 and the amount of carbon dioxide in the atmosphere.